your one-stop structural engineering consulting training institute that provides you with very detailed structural engineering analysis and design of various kinds of structures, reinforced concrete structures, timber structures, steel structures, either located onshore or located, in the sea, deep water, geotechnical engineering, and its like. Today we want to look at the design of a raft foundation for a two-story structure. What you can see on your screen is a two-story structure. We want to teach you how to design the raft foundation in compliance with BS 8004 and BS 8007, as well as BS 8110 Part 1 1997. So raft foundation design of a two-story structure, we concentrate on this, and then we explain what is required in design. So let's look very carefully. This is a two-story structure because you have that as the first floor level, and then that's the roof level. So you have the first floor level, and that's the roof level. This is the approach view. Okay, and then this is the ground floor plan. This is the ground floor plan. It's a 4-bedroom structure. There's 1 bedroom below. On the ground floor, you have 1 bedroom on the ground floor. It's all en suite with the bathroom. And on the first floor, you have 3 bedrooms. You have 1 master's bedroom with a jacuzzi and a closet, and then you have 2 other bedrooms. So 1 bedroom on the ground floor, 3 on the first floor. We are concentrating on design of the raft foundation for this structure because a visit to sites showed that the site location, it showed that the terrain was so bad. You had marshy soil, you have cohesive peaty soil. By universal classification system, it was classified that the soils has very high plastic properties, and then the soil is such that the bearing capacity is about 75 kilonewton per meter square. So it was decided by we, the structural engineers, to design a raft foundation for this structure. So this is the proposed main building, and then this is the ground floor profile, right? So this location is what you get to see here. That is location, and then that location is what you get to see on that side. So we want to design the raft foundation. We need to look at this very carefully. We start pro. Okay. Now this is structural layout. This is the foundation layout for that two-story structure. The structural foundation layout. Okay, so this is the superposition of the ground floor architectural layout on the proposed structural layout. So you could see the location of the ground beams. You have a ground beam on grid B, grid C prime, E prime, and F prime. Okay. So this is the approach to the structure. This is the foundation for the approach location. That's the columns. That's the columns, and then that's the column there. Okay. So that's the staircase. Look at section A. Section A shows you what's going on there. Okay, that's the staircase, and then those are the columns. We want to design this raft foundation structure to carry the entire loads, from the building. So the design is to design the raft foundation, okay, to carry the entire load from the building. Note very carefully that the design of superstructure has been done. We explained that in our subsequent videos. Is the reactions from the design of the superstructure. The reactions as serviceability limit states and ultimate limit states were used in design of the raft foundation. So let's look at how we proceeded in the design of the raft foundation. Okay, so this is the loading, the two-story structure. We want to look at the loading for the raft foundation quickly. The raft foundation is going to be subjected to its self-weight, the self-weight of the raft slab. The raft slab is 200 millimeter thick. It's 200 millimeter thick. Look at the description here. All raft foundation beams are 230 by 1.1 meters. That's all the grid beams. And then the raft slab panels are 200 thick. Okay, so all units are in millimeters. When we say 200, we mean that it's in millimeters. All units are in millimeters. The drawing has to be very detailed so that whoever's reading the drawing can implement carefully on site. Okay. So we look very carefully. The thickness is 200. So the self-weight of the thickness of the slab, raft slab, is 24 times that thickness is 4.8. The finishes. So you have, if you look at the structure, you have obviously you have architectural, you have the block work, and so you have the block work within the slab panels. So if you look carefully, you would see So these are the slab panels for the raft. Now within these raft panels, you have, obviously, you're going to have finishes. You're going to have screeding, okay, and obviously tiles based on the architectural design requirement. Okay, so those finishes, you need to apply the loads associated with those finishes. How do you get the loads? BS 6399 provides a provision. 6399 part 1. 6399 part 1 says that, okay, it says that in buildings where the use of other partitions as we say, an additional imposed load should be specified for floor area. So this imposed loads is being stated that should be applied on floor layers. Now, this may be taken as uniform distributed load of not less than 1/3 of the load. Okay, or where you have partitions for floor offices, this additional uniform distributed partition load should not be less than 1 kilonewton per meter square. So this is the partition load that is allowed for by the code. So finishes we took as 1 kilo per meter square, and then additional loads for wall partition was taken as 1.2. So summation of these loads gives the total dead load as 7 kilonewton per meter square. The imposed load is taken as 1.5 kilonewton per meter square. Imposed loads to capture walkway requirements taken as 1.5 kilonewton per meter square and obtained from the same code reference. The self weight of the raft beams, okay, is to be calculated automatically by STAAD so long as you model the raft beams correctly, and you specify its geometric properties and its corresponding density. 2 to 5 mm thick wall load, inclusive of rendering, is taken as 10.91. So this was calculated from the self weight of block work plus associated rendering on both sides. 13 mm rendering, self weight of block work is taken as 2.87 kilograms per meter square, plus rendering is taken as 0.3 kilograms per meter square. Add on both sides 0.6, that gives us 3.47, and the height of the block work is taken as 3.15. So if we look at the architectural design and we look at a section, it gives us the height of the block wall. Okay, if you measure this out directly, okay, so it gives us 3.15 kilonewton per meter square. So that's how we established that load. So let's look at how we did this in STAAD quickly. This is the entire structure. Look very carefully. This is the Raft foundation. Okay, that's Raft foundation. We could see carefully, if we explain this, you would see these are the grid beams corresponding to what we can see on the structural layouts. So you have grid B 1, 2, 3, 4, and 5. Sorry, that's the first floor. This is the foundation layout. So let's look at the grid beams. So you have 1, 2, 3, 4, and 5. These are the grid beams. Okay. If you look on STAAD, you can see the grid beams correctly. You can see the columns. This has to be modeled accurately. And this is the raft slab panels, properly discretized, and this is the staircase, longitudinal staircase coming from the ground floor up onto the first floor. So we model this accurately. These are modeled using the plate elements. So that's the raft slab panel modeled correctly. You ensure that your dimensional information is accurate. Okay, if we look carefully, we would see this is the raft beams. These are the dimensions of the raft beams. From point to point, we have them as shown in the structural details. So we have 3.22, 3.81, 3.61. So 3.22, 3.81, 3.61, and 4.02. It must be modeled correctly. So that is from there to there. So we check from here to here, that's 3.22, that to there, 3.81, from here to here, 3.69, and then from here to here is 4.02. Okay, so that's correct. The next thing is to assign your properties. So this is for the Raft beams. The Raft beams, look at very carefully, they are 1.1 by 230 as shown on the structural drawings. 1.1 by 230, 230 by 1.1. Okay, so we assign the properties to the Raft beams, and then we give the Raft beams the corresponding offsets from the slab. Okay, because in STAAD, members are modeled from centroid to centroid, so you would have to provide the corresponding offsets that the Raft beams make from the centroid of the slab. So if you look at the offsets are applied correctly from the centroid of the members, okay, downwards. So we have negative global coordinate system offset for the beams, okay, in the y direction, and then we have that for all the Raft beams. Okay, the next thing is to look at the loads. These are the loads we applied on the design of the Raft slab. The first one is the self-weight of the Raft slab. We said the self-weight is going to be calculated automatically by STAAD so long as we specified the self-weight load factor -1 in the y direction. The partition allowance, we talked about the partition. So there's going to be block work around where we have the Raft slab. All the partition allowance catered for at 1.2 kilonewton per meter square as specified in the load calculation was also applied. We also have finishes of 1 kilonewton per meter square. So these are the finishes also applied on the entire slab. And then this is the imposed load on the Raft slab, okay, due to walkway, human access. So human access, there'll be continuous human access on the ground floor. Okay, so this is the imposed load permitted by the code due to human access. Okay, then the staircase. So the staircase was designed together with the Raft slab. So you also have imposed loads on the staircase, okay, was applied together. Imposed loads on the staircase. The column loads. So these column loads are the column reactions from the design of the superstructure. So the reactions from design of the structure was done on a separate analysis file. So these are the various reactions. So these reactions are applied correctly, corresponding to the columns. So we can see them, you know, they were obtained from the analysis of the superstructure and it was applied accordingly. So these are the column loads under serviceability limit state consideration, and these are the column loads under ultimate limit state conditions. Okay, so the column load under ultimate limit state condition is automatically that's under serviceability limit state times 1.422. Okay, so load case 6 times 1.422 was used to get the ultimate limit state load combination. Ultimate limit state concentrated loads from the column. Then we do our load combination, which is dead load plus live load at serviceability limit state. Serviceability limit state factor of safety in accordance with the code of practice BS 8110 is 1.0. So you would have a 1.0 times all the corresponding dead loads. So these are dead. Look at 1, 2, and 1, 2, 4 are dead loads. So 1, 2, 4 are dead loads, and then 2, 5, and 6 are imposed loads. So we have the factors of safety, which is 1 times the corresponding dead and imposed. Then we do the same for ultimate limit state load consideration. Ultimate limit state load combination is 1 times load case 7, because load case 7 is already a factored ultimate limit state load. Okay, so you just repeat that same load case 1 times 1.7. When you do that, perform an analysis. When you run the analysis, you go to the post processor and look at the output. So when you do an analysis of a Raft slab, The first thing you want to look at is to ensure that the maximum earth contact pressure is less than the alignment bearing capacity of the soil. For this analysis, the alignment capacity of the soil taken for this analysis is 75 kilonewton per meter square. Okay, so when we look at, you go to plate, you go to base pressure, okay, apply. So start report the contact earth pressure beneath the raft slab. So we can see the contact earth pressure distribution carefully beneath the raft slab. We can see that the maximum values we are having is about 70.5 kilonewton per meter square around the slab edges, right? And we have it majorly distributed for about 26.4 kilonewton per meter square within the span, and we have between 48.5 and 52.9 around this region. So the earth pressure automatically varies significantly around the raft slab, and then but the maximum of all of this is about 70.5 kilonewton per meter square at the edges, and this is less than alignment bearing capacity of the soil. So the slab is satisfactory. Okay, so the raft foundation is satisfactory, and you then proceed with the structural design. Thank you very much for your time. Always follow us on this link, on this channel. We will be providing more information on various structural engineering design. Thank you.